Plasma, often referred to as the fourth state of matter, is a fascinating and complex form of ionized gas that makes up over 99% of the visible universe. Unlike solids, liquids, and gases, plasma does not have a fixed shape or volume, and its behavior is governed by electromagnetic forces rather than just thermal motion. In fact, plasma is so prevalent in the universe that it is estimated to be the most common state of matter. Did you know that the sun is essentially a giant ball of plasma, where nuclear fusion reactions occur at its core, releasing vast amounts of energy and light? This natural example of plasma showcases its immense power and potential. In terms of scale, plasma can exist on both astronomical levels, such as in stars and galaxies, and on microscopic levels, like in lightning bolts and fluorescent lights. The diversity of plasma environments is truly astounding. In laboratory settings, plasma can be created by heating a gas to extremely high temperatures or by applying a strong electric field to it. These controlled conditions allow scientists to study and harness the unique properties of plasma for various applications. For instance, plasma technology is used in industries such as semiconductor manufacturing, where plasma etching is employed to create intricate patterns on silicon wafers with high precision. The versatility of plasma in technology is further exemplified by its role in plasma TVs, where each pixel contains a tiny cell of ionized gas that emits ultraviolet light to produce vibrant colors. With such a wide range of applications and its omnipresence in the universe, plasma continues to captivate scientists and engineers alike, driving innovation and discovery in the field of plasma physics. The history of plasma physics is a rich tapestry woven with groundbreaking discoveries and remarkable individuals who have shaped our understanding of this unique state of matter. The journey of exploring plasma began in the late 19th century when Sir William Crookes, a British scientist, first observed the phenomenon of cathode rays in a vacuum tube. This discovery laid the foundation for the study of plasma and its behavior under varying conditions. In the early 20th century, Irving Langmuir, an American chemist and physicist, made significant contributions to the field by introducing the concept of plasma as a distinct state of matter. Langmuir's work on plasma oscillations and sheaths provided valuable insights into the behavior of charged particles in ionized gases. Another key figure in the history of plasma physics is Hannes Alfvén, a Swedish scientist who received the Nobel Prize in Physics in 1970 for his pioneering work on magnetohydrodynamics, MHD, and the dynamics of plasmas. Alfvén's research laid the groundwork for understanding the role of magnetic fields in controlling and shaping plasma in fusion reactors and astrophysical phenomena. As the field of plasma physics continued to evolve, researchers made significant strides in developing experimental techniques to study plasma in laboratory settings. One such milestone was the construction of the first tokamak fusion device in the Soviet Union in the 1950s. Tokamaks are toroidal magnetic confinement devices designed to achieve controlled nuclear fusion reactions by heating and confining plasma at high temperatures and pressures. Over the decades, tokamak experiments have yielded valuable insights into the behavior of plasma and the challenges of sustaining fusion reactions for practical energy production. In recent years, advancements in computational modeling and simulation have revolutionized the study of plasma physics, allowing researchers to explore complex plasma phenomena with unprecedented detail and accuracy. High-performance computing platforms have enabled simulations of fusion plasmas in tokamaks and other confinement devices, providing valuable data for optimizing reactor designs and predicting plasma behavior under extreme conditions. The fusion research community has also made significant progress in international collaboration, with projects like ITER, International Thermonuclear Experimental Reactor, bringing together scientists and engineers from around the world to work towards achieving sustained fusion energy. The history of plasma physics is a testament to human curiosity and ingenuity, driving us to unravel the mysteries of the universe and harness the power of plasma for the benefit of society and future generations. Plasma, as the fourth state of matter, exhibits unique properties that set it apart from solids, liquids, and gases. One fascinating characteristic of plasma is its ability to conduct electricity, making it an essential component in technologies such as plasma TVs and fluorescent lights. In fact, plasma screens in TVs can contain up to millions of tiny cells of ionized gas, each producing light to create vivid images. Another intriguing property of plasma is its responsiveness to magnetic fields. This property is harnessed in fusion research, where magnetic confinement devices like tokamaks use strong magnetic fields to control and stabilize the hot, ionized plasma. The behavior of plasma is also influenced by its temperature and density. For instance, in fusion experiments, plasma temperatures can reach millions of degrees Celsius, exceeding the core temperature of the Sun. The high temperatures are necessary to overcome the electrostatic repulsion between positively charged nuclei and facilitate nuclear fusion reactions. Plasma density, on the other hand, plays a crucial role in determining the efficiency of fusion reactions. Achieving high plasma densities is essential for increasing the rate of fusion reactions and maximizing energy output. Plasma also exhibits collective behavior, known as plasma waves, which propagate through the ionized gas and can be used to study the properties of the plasma. These waves play a significant role in plasma heating and particle acceleration processes. Understanding the properties of plasma is essential for advancing fusion energy research and developing new plasma technologies. With its diverse and intriguing characteristics, plasma continues to captivate scientists and engineers, driving innovation and discovery in the field of plasma physics. Plasma, the fourth state of matter, is not only prevalent in laboratory settings and technological applications, but also abundant in nature, showcasing its diverse and fascinating properties. One of the most striking examples of natural plasma phenomena is the auroras, also known as the northern and southern lights. These mesmerizing light displays occur when charged particles from the sun interact with the Earth's magnetic field, creating colorful curtains of light in the polar regions. Did you know that the temperature of the plasma in auroras can reach up to 4,000 degrees Celsius? This extreme heat is responsible for the vibrant hues of green, red, and purple that dance across the night sky. Lightning is another natural occurrence of plasma, where electrical discharges ionize the air, creating a brief but intense burst of plasma that can reach temperatures hotter than the surface of the sun. In fact, a lightning bolt can heat the surrounding air to temperatures of about 30,000 degrees Celsius, causing it to expand rapidly and produce the characteristic thunderclap. Plasma can also be found in space, where it makes up the majority of the visible universe. Stars like the Sun are essentially giant balls of plasma, where nuclear fusion reactions generate immense heat and light. The solar wind, a stream of charged particles emitted by the Sun, creates a vast region of plasma known as the heliosphere, which extends far beyond the orbit of Pluto. These natural examples of plasma in auroras, lightning, and space highlight the dynamic and awe-inspiring nature of this unique state of matter. Plasma, with its unique properties and versatility, has found a wide range of applications in various technological fields, revolutionizing industries and driving innovation. One fascinating application of plasma technology is in the field of medicine, where plasma sterilization is used to decontaminate medical instruments and equipment. Unlike traditional sterilization methods that rely on heat or chemicals, plasma sterilization is a cold process that effectively kills bacteria and viruses without damaging sensitive materials. This method has become increasingly popular in healthcare settings due to its efficiency and eco-friendly nature. Another intriguing use of plasma technology is in the production of nanomaterials. By subjecting gases to plasma conditions, researchers can create nanoparticles with unique properties and structures that are not achievable through conventional synthesis methods. These nanomaterials have applications in electronics, catalysis, and biomedicine, offering new possibilities for advanced technologies. Plasma technology has also made significant advancements in the field of environmental remediation. Plasma reactors can be used to treat contaminated water and air by breaking down pollutants into harmless byproducts through chemical reactions induced by plasma discharges. This environmentally friendly approach has the potential to address pollution challenges and improve the quality of air and water resources. In the realm of aerospace engineering, plasma technology plays a crucial role in developing advanced propulsion systems for spacecraft. Electric propulsion engines, such as Hall-effect thrusters and ion thrusters, use plasma to generate thrust by accelerating charged particles to high velocities. These engines offer greater fuel efficiency and longer operational lifetimes compared to traditional chemical rockets, making them ideal for long-duration space missions. The semiconductor industry also relies heavily on plasma technology for manufacturing integrated circuits and electronic devices. Plasma etching and deposition processes are used to pattern and coat semiconductor wafers with high precision, enabling the production of smaller and more powerful microchips. In fact, nearly 80% of all semiconductor manufacturing processes involve some form of plasma technology. The impact of plasma technology on the global economy is substantial, with the market for plasma-based products and services estimated to be worth billions of dollars. The growing demand for plasma technologies in diverse sectors, including healthcare, electronics, and aerospace, underscores the importance of continued research and development in the field of plasma physics. As we look to the future, the potential applications of plasma technology are limitless, offering new possibilities for sustainable energy, advanced materials, and space exploration. Fusion energy, often hailed as the holy grail of sustainable power generation, holds the promise of clean, abundant energy with virtually no greenhouse gas emissions. One of the most ambitious fusion energy projects is ITER, an international collaboration involving 35 countries, with the goal of demonstrating the feasibility of fusion power on a commercial scale. ITER's tokamak reactor, currently under construction in France, is designed to produce 10 times more energy than it consumes, a crucial step towards achieving a self-sustaining fusion reaction. The sheer scale of the ITER project is impressive, with the reactor weighing 23,000 tons and containing over 1 million components. Once operational, ITER is expected to generate 500 megawatts of fusion power for up to 500 seconds, marking a significant milestone in fusion energy research. Beyond ITER, private companies like TAE Technologies and Commonwealth Fusion Systems are also making strides in developing compact fusion reactors based on innovative plasma confinement concepts. These next-generation fusion devices aim to deliver practical fusion energy solutions that are cost-effective and scalable. In the quest for fusion energy, researchers are exploring advanced materials and technologies to withstand the extreme conditions inside a fusion reactor, such as high temperatures and intense neutron flux. Materials like tungsten and beryllium are being investigated for their resilience to neutron bombardment and heat loads, ensuring the long-term viability of fusion power plants. With the potential to provide a virtually limitless and environmentally friendly energy source, fusion energy represents a transformative solution to the world's growing energy needs and climate challenges. Plasma technology has revolutionized the field of materials processing, offering innovative solutions for manufacturing and surface modification. One fascinating application of plasma in materials processing is plasma nitriding, a surface hardening technique that enhances the wear resistance and durability of metal components. By exposing metal parts to nitrogen plasma at high temperatures, a nitrogen-rich layer is formed on the surface, significantly improving the mechanical properties of the material. Plasma nitriding is widely used in industries such as automotive, aerospace, and tooling, where high-performance components are required to withstand harsh operating conditions. Another intriguing application of plasma technology is plasma spraying, a versatile coating process that deposits thin films of ceramics, metals, or composites onto various substrates. Plasma-sprayed coatings offer superior wear resistance, thermal insulation, and corrosion protection, making them ideal for applications in turbine blades, medical implants, and electronic components. The global market for plasma-sprayed coatings is projected to reach over $2 billion by 2025, driven by the demand for advanced surface treatments in key industries. Plasma technology is also employed in plasma etching, a precise and selective process used in semiconductor manufacturing to pattern microelectronics devices. Plasma etching allows for the creation of intricate features on silicon wafers with submicron accuracy, enabling the production of smaller and more powerful integrated circuits. The semiconductor industry relies heavily on plasma etching processes, with over 70% of all microelectronics devices undergoing some form of plasma treatment during fabrication. The continuous advancements in plasma technology are reshaping the landscape of materials processing, offering new possibilities for enhancing the performance and functionality of a wide range of products. Plasma physics research presents a myriad of challenges that push the boundaries of scientific understanding and technological innovation. One of the key challenges in fusion energy research is achieving sustained plasma confinement and stability. Plasma instabilities, such as disruptions and edge-localized modes, ELMs, can lead to the loss of thermal energy and particle confinement, hindering the progress towards achieving a self-sustaining fusion reaction. Researchers are actively exploring advanced plasma control techniques and magnetic confinement strategies to mitigate these instabilities and improve the performance of fusion reactors. Another significant challenge in plasma physics research is understanding the complex interactions between plasma and materials. Plasma-facing components in fusion reactors are subjected to extreme heat fluxes and particle bombardment, leading to material erosion and degradation over time. Developing materials that can withstand the harsh conditions inside a fusion reactor is crucial for ensuring the long-term viability of fusion energy. In addition, plasma turbulence remains a fundamental challenge in plasma physics, affecting the efficiency of energy confinement and heat transport in fusion devices. High-performance computing simulations are used to study turbulent plasma behavior and optimize plasma confinement strategies for future fusion reactors. The interdisciplinary nature of plasma physics research requires collaboration between physicists, engineers, and material scientists to address these challenges and drive progress in fusion energy and plasma technology. With continued research and innovation, overcoming these challenges will pave the way for realizing the full potential of plasma physics in advancing clean energy solutions and materials processing technologies. The future of plasma technology holds immense promise for revolutionizing various industries and scientific fields. With the development of advanced plasma diagnostics and modeling techniques, researchers are gaining unprecedented insights into plasma behavior and interactions. In fusion energy, projects like ITER aim to demonstrate the feasibility of commercial fusion power, with the potential to provide clean and abundant energy for future generations. The global market for plasma-based products and services is projected to reach over $16 billion by 2025, driven by the demand for plasma technologies in healthcare, electronics, and aerospace. Plasma-based materials processing techniques, such as plasma nitriding and plasma spraying, continue to evolve, offering enhanced performance and durability for a wide range of applications. As plasma physics research advances, the prospects for harnessing the power of plasma in innovative ways are brighter than ever. The field of plasma physics and its applications offer a fascinating glimpse into the intricate workings of the universe. Did you know that plasma makes up over 99% of the visible universe, showcasing its prevalence and importance in natural phenomena? In fusion energy research, projects like ITER aim to generate 500 megawatts of fusion power for up to 500 seconds, marking a significant milestone in the quest for sustainable energy solutions. The global market for plasma-based products and services is projected to reach over $16 billion by 2025, highlighting the growing demand for plasma technologies across industries. With advancements in plasma technology and materials processing, the future holds exciting possibilities for leveraging the unique properties of plasma to drive innovation and address pressing challenges in energy, healthcare, and materials science.